Hello everyone, I'm Yaoyao. I will talk about our work, Wakening past concepts without past data, class incremental learning from online placebos. It is joint work with Yingying, Bernt, and Qianru. Class incremental learning aims to learn new data by incrementally updating a model trained on previous data. In the first phase, we train the classifier using data 1, and after that, we evaluate the classifier on the corresponding test set for data 1. In the second phase, due to the memory limitation, we cannot keep all samples in data 1. We select example 1 from data 1, and we get data 2. We update the classifier and conduct the evaluation on all concepts the classifier has learned so far, which is the standard setting. So that means in phase 2, we learn the classifier on example 1 and data 2, and finally, we evaluate the classifier on the test set for both data 1 and data 2. And the same goes for the third stage and so on. So the main challenge for class incremental learning is the catastrophic forgetting problem. The classifier overfits new data and forgets the old knowledge. To overcome this problem, distillation loss is widely used to retain old knowledge and overcome forgetting. So, however, there is a conflict between the distillation loss and the cross-entropy loss if we directly use the new data to compute the distillation loss. On the left, we provide a conceptual figure to show this. The dark blue and orange numbers denote the predictions of old class and new class, respectively. It is clear in figure A that the objectives are different when using a new class sample for distillation. For example, the ground truth label for the second old class is 0, while the distillation loss label at this position is 0.8. This is not an issue when using the old class sample. For example, in the figure B, its ground truth label and distillation loss label have consistent magnitudes at the same position. They are 1 and 0.7 respectively. Here, our idea is to select the unlabeled samples and compute the distillation loss on this data. The benefits of our method are as follows. First, there is no depreciation for new class performance. Second, no additional supervision is required. Third, our method is very easy to train. In the following, we show how to use our method in phase I of an incremental learning system. At the beginning of this phase, we build phase-specific evaluation functions to select unlabeled data. During training, we select placebos as follows. First, we load an unlabeled data batch U from the free data stream. Second, we compute the scarce using the evaluation functions for all samples in U. And for each old class M, we select case placebos with the highest score and add them to the placebo set P. And then we can sample a placebo batch P from the placebo set P, capital P. In the next, we can sample the new class batch D and old class batch E from the target data stream and memory, respectively. Then we use the new class batch B and old class batch C to compute the cross-entropy loss. And we use the old class batch C and the placebo batch P to compute the distillation loss, that is KD loss in this figure. So this is our method, and in the following, I'm going to show some visualization result and also our performance. In this slide, we show the visualization result. Figure A demonstrates the activation maps visualized background cam for the placebos of old classes on CIFAR 100. The two classes are road and table. We use ImageNet 1K as the free data stream. We can see that the selected placebos contain the parts of road and table, even though their original labels on ImageNet 1K are totally different classes. While this is not always the case, our method seems to find efficiently related images to old classes that active the related neurons for old classes. And B shows the t-SNE result for placebos, old class data, and new class data. We can see that the placebos are located near the old class data and far from the new class data. This is why placebos can recall the old knowledge without harming the new class performance, new class learning. This table shows the average and last phase accuracy for 5 baselines. Learning without forgetting LWF, Icon, Lucille, AA-NET, and Foster. From the table, we make the following observations. Using our placebo CIL boosts the performance of the baselines clearly and consistently in all settings, indicating that our method is generic and efficient. When the number of exemplars decreases, the improvements brought by our method becomes more significant. And also, our placebos can boost the performance for all distillation terms. That is not only for the logic-based distillations and also for the feature-based distillations. For more details, you can visit our project website. Thank you for listening, and we are happy to answer questions.